In this video, I'm going to teach you how you can use the fundamental theorem of algebra to help you solve any polynomial equation. Now I'm going to use a set of guided notes that is going to just help me kind of with some of the writing so I don't have to kind of write it by hand, and that kind of slows down the video. So I really expect that when you guys take the notes, please do write down all the words that you do see along with how I'm filling in the blanks, just because you can pause and you can write them probably a lot quicker than I can write them with my finger on an iPad. So the key concept that we're going to kind of focus on is if you were to count all of the real and imaginary solutions, including repeated solutions, every nth degree polynomial will have exactly n zeros or n solutions. So what does that mean? Well, basically, if you look at example 1 with me, you can answer questions like how many solutions do you expect each of the polynomials to have if you were to count all repeated and real imaginary solutions all together. Well, basically what it's saying is this, guys. As long as you know the degree of the polynomial, which when I look at part A, for instance, I know the degree is the highest exponent. If my degree is 7, that's like my n value, I know that there's got to be a total of 7 solutions. That's, again, if I were to count all real, all imaginary, and repeated solutions to this polynomial. If you look at part B, now I made this one a really crazy looking polynomial, but nonetheless it's a polynomial. The highest exponent that you see hopefully here is 101, so that would be a 101 degree polynomial. If we were to try to solve this, it would have 101 total number of solutions. Now, luckily for all of us, we're not going to even come close to messing anything with that high of a power, but just to drive home the point. If you look at C, the degree is n, so it would just have n solutions. So that's the first most important thing to realize as we go forward solving equations that involve polynomials. The degree gives you the number of solutions. Now from here, these are very, very important steps that you're going to follow for pretty much the rest of the chapter. That's going to help you find all of the zeros of a polynomial function. So when you're trying to find all of the zeros of a polynomial function, there's a few steps that you need to take. And it is really important, guys, that you write these 3 steps down and have them down pat so that you can kind of solve these problems. And I'm going to work through a few examples with you so you know how to kind of apply them. The first thing is you're going to make sure that the polynomial is written in standard form and always set equal to 0, kind of like we've already been practicing. Then the second step is see if you can factor the polynomial. You've already learned how to factor polynomials, so this is actually going to be the fastest and easiest way to solve if it's at all possible. So if you can, you're going to factor completely and use the zero product property. If it's not factorable, you're going to go to step 3, and you're going to use your graphing calculators to help you graph the function to find its zeros. Then you're going to use synthetic division to divide out each of the zeros to find any remaining factors and zeros. So you will need to have your graphing calculators handy as we go forward in this lesson. Now before we kind of get there, take a look at these 3 examples where I want to find all of the solutions. For part A, I have x cubed equals 0. Well, this is pretty simple. First of all, it is a polynomial set equal to 0, so step 1, check, that's done. Step 2, I think I can factor that. Actually, it's so easy that x cubed is literally just x times x equals 0. That means any one of these factors of x can equal 0 to make this true. So, in fact, I can solve this by factoring and using the zero product property. And what I get is 3 solutions, although it's repeated solutions. Those solutions are 0, 0, and 0. So I think the way when you guys do your your exit quizzes, this might be called 0 with a multiplicity, and for short they'll just say 0 mult of 3. That just means 0 shows up 3 times. Okay, if you take a look at a part B. Now here's a polynomial equation set equal to 0. Actually, it's a quadratic, right? The degree is 2. And I think we might be able to factor this. I know the first term is a perfect square of x, and the last term, 49, is a perfect square of 7. And if I were to multiply x and 7 together and double that, I think I would get 14x, which matches the middle term. So this is actually a perfect square trinomial. The sign in the middle, because that's a negative, would make this negative. So this factors into just x minus 7 squared equal to 0. I don't need to use a graphing calculator. I can solve this by factoring. It really is x minus 7 times x minus 7 equals 0, since it's x minus 7 squared. So if I apply the zero product property and set each of these factors equal to 0, each one's going to give me a 7. Now here is where I have 7 repeated twice. This would be 7 with a multiplicity of 2. This third example, if you look at C, it is set equal to 0. Now I'm going to try to factor this, and when I factor, I look for a GCF, but I don't have any greatest common factor. But I do know that I have 1, 2, 3, 4 terms. So hopefully you're thinking just like I am right now. I can factor this guy by grouping. So I'm going to pair the first 2 terms and the last 2 terms together. Out of the first 2 terms, I can pull out an x squared, leaving behind x plus 3. Out of the second 2 terms, I think I can pull out a 16, and that would leave behind x plus 3 as well. Now, I have x plus 3's that match, so that means I can pull out the factor x plus 3, and I'm left with x squared plus 16. And remember, this is set equal to 0. I can't factor x plus 3 any further, so if I set x plus 3 equal to 0, I get one solution at negative 3. Now, a lot of students see x squared plus 16 and they think, ooh, I can probably factor that more. It looks like 2 of those are squares. X squared is a perfect square and 16 is a perfect square. But there is no factoring a sum of 2 squares. That sign would need to be a subtraction sign to make it a difference of squares to go further. So I'm actually stuck. But what I could do is set x squared plus 16 equal to 0. And since I just have an x squared term, what I'm going to do is solve by taking square roots. I'm going to subtract 16 and get x squared equals negative 16. And when I square root, I get just x equals plus or minus. Remember, when you square root, I can poke out an I, and the square root of 16 is 4. So that's better written as plus or minus 4i. So in all, guys, if I were to list all 4 solutions, I would have, excuse me, not all 4 solutions, but I would have negative 3 as a solution, 4i, and negative 4i, which, by the way, there's 1, 2, 3 solutions that matches the exponent 3. I was expecting to get 3 solutions. So these are 3 examples where I did not need to use my graphing calculator. As a matter of fact, it's just a review of things you probably already knew how to do. Now, before I show you how to use a graphing calculator, there's a couple very interesting and important things to keep in mind that we're going to look at next. So the thing we have to kind of discuss next, guys, is when we look at the graph of a polynomial function, just looking at the graph and interpreting how the graph intersects the x-axis tells us a lot about the zeros of that polynomial and about repeated solutions in particularly. So what I'm going to do is talk about each of these cases very specifically, guys. So when a graph has exactly 1 0 at the x-axis, it'll look something like this. So let's just make a sketch. Let's say this is your y-axis and this is your x-axis. Again, this is just a loose sketch. If you have a graph that does something like, I don't know, like this, like that, let's say, when you graph it, you'll notice that the graph slices right through the x-axis just at one point. And let's just call that, let's say this is like 1, 2, this happened to be right at x equals 3. This is just one solution where the graph hits the x-axis at 3. The way I refer to this, guys, I call this a cut, meaning the graph just cuts right through the x-axis at one spot, and that means there's no repeated solutions. It's just 3. And actually, I think if we were to have graphed x cubed plus 3x squared plus 16x plus 48, it probably does something like this. This is the problem we just solved in the previous page, where I think the one answer was, geez, I hope my memory's serving me right. If you look back, I think it was 3, or it might have been -3. But either way, that was the one real solution. Then I think it was like 4i and -4i. Guys, when you get imaginary solutions like these two jokers, that's not going to show up on the real axes. This is not the complex plane. This is just real numbers on the y-axis, real numbers on the x-axis. So the imaginary solutions don't show up when you graph. So imaginary ones you're not going to see. Only real solutions will you actually see when you're graphing. Now, on the other hand, do you remember we solved x squared minus 14x plus 49 on the previous page, and I think we got x equals 7 with a multiplicity of 2, meaning it repeated twice. If you were to graph that one, you'd get something like this. Let's say this is our y-axis, and this is our x-axis. Again, this is just a loose sketch, obviously. I'm not using like a ruler to do this. But if we were to graph that, the parabola opens up and actually does something like this. That's a little different than the previous one. The parabola comes down and it would just kiss the x-axis at 7. It doesn't cut through. It touches, but then it goes back up. I call this particular type of intersection a kiss. Meaning, it's almost like if you were kissing somebody on the cheek, you approach the cheek. If you think of the x-axis, right, as your cheek, you approach the cheek, you give it a little kiss, and then you pull back away. You don't go through the x-axis or you don't go through the cheek. You just kiss it for a moment, and then it goes back. When you see a graph kiss the x-axis, that means wherever it kisses, like here at 7, there's going to be an even number of repeated solutions. Meaning, like for this example, there was not just one 7, there was 2 7s. That's an even number, right? Don't get caught up, guys, with the fact that, the actual solution itself, 7, is an odd number. That's not important. What's important is that there were 2 7s. That's repeated twice, right? Now, let's go to the last example I want to talk about. If I have x cubed equals 0, remember how we got x could be equal to 0, 0, and 0? I had like an odd number of repeats at 0. There's 3 of them. The graph here, if you were to do it, does something else that's very bizarre and interesting. The graph starts low, it flattens out like it's going to kiss, right? Just like the previous example, but it doesn't pull back down. It kisses, it flattens out, and then it keeps on going up. It actually goes through the x-axis. So here, where it hit at 0, I call this a kiss and go. This kiss and go, meaning it doesn't just kiss, it kisses and keeps on going through the x-axis. When that happens, there's going to be an odd number of repeats. Meaning there are like 3 there, or could be 5, and so on. So that's important to keep in mind as we go forward. Now what I'm going to do is just kind of go through a few examples with you. Okay, let's do a few examples of really the core of what we're trying to get at. We're going to try to find all the zeros of the functions or roots of the functions and solve. So the first thing I'm going to do when I look at A, for instance, is see, first of all, is it in standard form set equal to 0? Yes. Goes from highest to lowest degree, set equal to 0, that's good. Second, can I factor it? Well, I think I might be able to group it. There's 4 terms, but before I group, I do see that I can take out an x. So if I factor out an x, I'll be left with x cubed inside plus 6x squared plus 12x plus 8 equal to 0. So what I'm going to now do is see if I can go further on this guy. Now, if I do that, I'm going to have to pair up the first two terms, x cubed plus 6x squared, and then I have to pair up the last two terms, 12x plus 8, and see if I can factor by grouping. From these two, the GCF is x squared, leaving behind x plus 6. From these two, GCF I think is 4, which leaves a 3x plus 2. Wait a second, this is not good. The x plus 6 and the 3x plus 2 do not match. So I'm stuck. This is a dead end. I can't do anything more with that, so I can't factor that. There is some good news though. Let me erase this to get it out of the way. There is some good news. I already know one solution here. And actually, that one solution, if I use the zero product property just where I have this factored, I know I can set x equal to 0, and I can set this whole mess, x cubed plus 6x squared plus 12x plus 8 equal to 0. This is one solution. But keep in mind, my degree is 4. There's 3 more solutions to this guy. And guess what? They're hidden in here. Look at the degree. It's an x cubed, meaning there's 3 solutions left there. If I add the 3 solutions I get there to this 0 that I have, I'm going to get my total 4 that I expected, right? So what we're going to focus on now, guys, is we're going to see if we can solve this cubic polynomial, that degree 3 polynomial. Now I couldn't factor it, so this is where I need to use my calculator. So guys, when I use the calculator and bring it up on the screen, unfortunately it's going to erase what I just wrote down. Obviously you're going to have that written down, so please make sure you have written down the x cubed plus 6x squared plus 12x plus 8, and I'm going to show you what to do now with our graphing calculator to help us with this. Okay, so let's see if I can do this. And as promised, it disappeared. Now I'm going to bring up my calculator, right? And let me turn it on. The first thing you're going to do, guys, is go to y equals. Press y equals on your calculator. This is where you can edit in and enter in the function you want to graph. So I believe the thing we wanted to graph was x cubed. To type in x, you have to hit that the button just to the right of the alpha key, where it has like a x, a t, and then like this weird circle looking thing that's called theta. That button, if you hit it, an x will pop up. And now I want to do x cubed. So I'm going to raise it using the caret symbol, raise it to the third, and then I have to type in plus 6x squared. You can use the squared symbol for squaring, and then I'm going to hit plus 12x and then plus 8. That's the function I wish to graph. Now, what I'm going to have you try to do is always graph in the standard window. If you click on the window button, which is right next to y equals, okay, you're going to see the following pop up. Your x min should be at -10, x max is 10. Guys, that just says the smallest value of x and the largest value of x goes from -10 to 10. The x scale is just what you're counting by. On the x-axis, it's going to count by ones. Y min is -10, y max should be 10. That's the lowest on the graph, and the highest on the graph is from -10 to 10, and the y scale is 1. We should want to leave that. If that's set, how it looks here, hit graph, that button all the way on the right, and you should see the following. Now, what's interesting here, on this graph, to me, it does look like it hits the x-axis, but in a very special way. It looks like it's that kiss and go. Let me make sure. I think I might have cut out there it just stopped. Let me go back. I apologize sincerely, as this technical difficulties. So what it appears as if you hit graph and you get this on here, guys, the it looks like it's kissing and going at -1, -2. Now, I don't want to just kind of guesstimate it hits the x-axis at -2. The way you're going to verify this, guys, if you hit the trace button, oops, got to turn my calculator. If you hit trace just under the calc button, if you hit trace and you literally type in the x value that you think you're going to hit, and I think I hit at -2. I'm going to type -2, and as you type that, you'll see it pop up on the screen. Hit enter, and it takes you to where x is -2 on your graph. Notice where it says when x is -2, I get y is 0. This is really important that it said y is 0. That means that's where it hits the x-axis. That also tells me that there's an odd number of these -2's because it's a kiss and go. Remember, kiss and go. There's an odd, let me see if I can write the odd number of repeated solutions. So what that tells me is there's not just one -2 there, there's going to be a -2, a -2, and a -2. I don't have to do anything else fancy. There's the 3 solutions for that cubic polynomial I graphed, plus, remember 0 was the other one? There's all 4 solutions total that I was expecting. I want to do another one. I know this is a long video, but I do think it's worthwhile doing another example or 2 even with you guys. Again, everything's going to erase as I kind of change the screen here, so bear with me for a second. Let's go like this. Alright guys, check out this next example here. Look at B. I have 1, 2, 3, 4, 5 terms. It's in standard form, it's set equal to 0. There is no GCF. I can't group this. We've never even factored things with 5 terms. I do know that there are 4 solutions because that is my degree. What I'm going to do right away is just use my calculator, and hopefully we can find all 4 solutions just looking at the calculator. Let's see what happens. So let me bring up my calculator. When you do this, we want to type in y equals the exact polynomial. So I'm going to use x raised to the 4th plus 3x raised to the 3rd minus 8x squared minus 22x minus 24, and I'm going to hit graph, and that's what I see. Now let me explain a couple of things to you guys. First of all, it looks like 2 lines were just graphed. This is not just 2 lines. Keep in mind, we're graphing a polynomial that has a degree 4, right? It's an even degree and a positive 1 leading coefficient. If you think of the end behavior, you know it's going to go up and up. And that is what's going on. The bottom part of the graph, though, we can't see because remember, the bottom of our screen only goes down to -10. I bet the graph really goes like this and does something funny, you know, and it is connected, but we don't see any of that stuff. All we're looking at on our screen is like this kind of a picture, okay? And I'm not really worried about all this nonsense going on down there. The only thing that interests us guys, and you have to focus on this, the only thing that we care about are these intersections of the graph with the x-axis. Now, if you think about it and you look closely at your graph, to me this looks like a cut, and this also looks like a cut. It's only hitting once there. There's no repeated solutions. There's no fancy kissing or kissing and going. And it looks to me like this one is at x equals 3, and it looks like this one over here is at x is -4. And I'm going to double check that by using the trace and typing that in my calculator in just a second. Let me erase this so we can see what happens here. Okay, let's go back to my calculator. I know that just got erased, but it has to with the technology that I'm using. So I'm going to hit trace, and I think I hit at 3, so I'm going to type in x is 3 just by hitting the number 3 and hit enter, and it is verified. When I plug in 3 for x, I get 0 for y. Let's check -4. I'm going to type -4, not -4, but -4, hit enter, and yep, I get a 0. So that means the following. Let's kind of exit the drawing and let's use what we know. I know I have a solution at x equals 3 and x equals negative 4. Those were just cuts. Those weren't repeated solutions. So there's 2 out of the 4 solutions. By the way, the other 2 I know must be 2 imaginary solutions, because if they weren't imaginary, they would have shown up on my graph. But I only have this one and this one. That's only 2 out of the 4 solutions. So what we're going to do now is go to step 3. We're going to synthetic divide out these zeros and see if we can factor the rest of that remaining polynomial. So check this out. This is what we're going to do. Synthetic divide with the 3. And it doesn't matter which one you pick first. I'm going to synthetic divide it with the 3. And I'm going to do all of the coefficients. 1x to the 4th, 3x cubed, negative 8x squared, negative 22x's, and then a negative 24 was on the end. Now I drop down the 1, and I multiply by 3, I get 3. I add, I get 6. If I multiply that by 3, I get 18. And if I subtract 8, I get 10. If I multiply that by 3, I get 30. When I add, I get 8. When I multiply that by 3, I get 24. When I add, I get 0. By the way, you better get 0, because 3, remember, is a 0. We should get 0 at the end. Now, this is the other thing that we have to kind of keep in mind. These are the coefficients of the quotient polynomial, which I'm going to go ahead and just divide out my next 0 right away. So I'm going to synthetic divide twice with a negative 4 this time. The coefficients I'm going to synthetic divide with are 1, 6, 10, and 8. I'm going to drop down the 1, multiply by negative 4, and I add, I get 2. If I multiply that by negative 4, I get negative 8. When I add, I get 2. When I multiply by negative 4, I get negative 8. When I add, I get 0, which again is the expectation. We should get 0. This negative 4 is a 0. So this is the important remaining coefficients of my quotient polynomial. 2 is the constant. This is the x coefficient. This is the x squared coefficient. So I have x squared plus 2x plus 2 that I'm going to try to solve and set equal to 0. Now, to do this, I'm not going to be able to factor, so I'm going to have to use maybe the quadratic formula or completing the square. If I use quadratic formula, it's going to be negative b, or negative 2, plus or minus the square root. B squared is going to be 2 squared minus 4 times the a value 1 times the c value 2, all over 2 times the a value 1. So let's simplify. I get negative 2. You can hear my baby getting ready for her bath. I apologize. 2 squared is 4. And then 4 times 1 times 2 that's going to be a negative 8. And that's all over 2. So I end up with negative 2 plus or minus the square root of negative 4 over 2. That's negative 2 plus or minus 2i all over 2. Now I can divide each of these by 2, right? So negative 2 divided by 2 is negative 1. 2i divided by 2 is 1, so I get negative 1 plus or minus i. So at the end of the day, guys, these are my solutions. I have 4 of them. I have negative 4, 3, and then I got negative 1 plus I and negative 1 minus I. There's altogether 4 solutions there. I'm going to definitely stop there because I don't want to ever make a video that's longer than 30 minutes, and I'm almost there now. I'm going to make another supplementary video where I'm going to do 2 more examples for you, for your enjoyment, should you need to see another couple on how to do this with a calculator. Thank you very much for watching. This is probably the biggest and most important lesson of the chapter. So, hopefully this was worthwhile, and thank you very much for watching, guys.